This is a recording for the airtrack portion of this lab on forces, and this is how it works. There's an airtrack here with a wagon or a bob on top, and then there is a string, and technically this is a pulley, and then there is a mass hanging here. So when you start it, that mass here will accelerate itself and the bob, pulling it along. The way the airtrack produces for the wagon or the bob to glide along is by blowing air into it. So you would have to imagine that the simulation is really loud, and actually that's the way it is in my classroom. It's really loud. Okay, I'm going to go over to explaining what we're actually going to measure here in just a moment. So here on the airtrack, what we have is we have a mass for the wagon or bob that is 100 grams, and then we have the mass of the hanger here, which is 1 grams, but I will increase that to 2, 3, 4, and 5 grams, so we will get different measurements. And this one here is the only force that is applied, so the weight of the hanger pulls the wagon along. We're gonna do two different computations. One of them is the theoretical one of how fast it should be accelerated, and the other one is the measured one. So this is the way it looks on the lab sheet. It says in a lab experiment, it's actually rather difficult to confirm Newton's second law, the net force equals mass times acceleration, for moving objects, because at least one of the forces is friction and or air resistance, hence the air track. Take measurements at this website that I accessed to measure the acceleration in two different ways. One of them is the kinematic equation that you find in your book. So distance equals 1/2 acceleration over time squared, and that would resolve itself, of course, into acceleration equals 2 times distance over time squared. And compare that to the computed acceleration from Newton's second law for this experiment, which is the net force. As I said, the only force applying here is the hanger's weight, so mass of the hanger times gravity, and that equals the mass that is being accelerated, which is the two actually together. Both the hanger and the bob or wagon are connected by a string, so both of them are accelerated together. Well, and that produces that acceleration that we have to determine. I call this one actually the theoretical acceleration, because that's how much it should be. So that acceleration is going to be mass of the hanger times gravity divided by mass of the hanger plus mass of the bob. The other one, this one here, I call the experimental acceleration, because in a real lab, for of course it's just a simulation, we would measure the distance, we would measure the time, and then figure out how much acceleration we have. And I just noticed that this was a little bit off the recording here. So here's the theoretical acceleration from Newton's second law. Here's the experimental acceleration from the measured distance and time. The distance itself is fixed throughout the experiment at 0.5 meters. The mass of the wagon I will keep fixed at 100 grams. That's why I wrote them on top. Okay, so let's get some data. So here it starts, and I get 3.209 seconds for 1.0 grams. Then I'm gonna change this to 2.0, and for 2.0 grams I get 2.280 seconds. Then 3.0 seconds. I do this really similar in the face-to-face lab, 1.871 seconds. It's pretty much just me doing it, besides I also just have one air track anyway. And then for each mass I actually take 5 measurements, because, well, those are real measurements. This one here, of course, is a simulation, and you can check this out yourself, that if you take a second measurement for 4.0 grams, you come up with 1.628 seconds again and again and again, because they wrote this applet to give perfect numbers, so to say. Okay, 5.0 grams is going to be the last one, and that's 1.463 seconds. And when we look at the data, well, obviously it became faster and faster. The acceleration increased, which made the time shorter and shorter. And now we're going to calculate the acceleration. First, I'm going to calculate the theoretical acceleration. So as I said, it's the mass of the hanger, 1.0 grams times 9.8 meters per second squared, divided by 100 grams for the hanger plus 1.0 grams for the 100 grams for the bob, 1.0 grams for the hanger. By the way, I don't have to convert the grams to kilograms because I have grams right here and I divide by grams here, so those two units divide, and so it doesn't matter if I have grams or kilograms or ounces. And what survives is the unit for the acceleration, meters per second squared. So the first one I'm going to come up with 0.097, and then it should be getting faster. 2 grams, and I have to change this one here too. 2 grams, so 2 grams are pulling 102 grams now. Now 3 grams. Okay, I will edit them here on the side. And I got 2 more, 4 grams. And 5 grams. There we go. And now I do the experimental acceleration, which is 2 times the distance of 0.5 meters, divide by the time squared, 3.209 squared, and then it's going to be divide by 2.280. Oops. Oh no. 0.5 divided by 2.280. There we go. And so on. 1.871. And a couple more. 6 to 8. And 463. You might have that on your calculator too, this second entry button that you can access the last calculation you did. So the outcome is that these are the experimental accelerations and these are the theoretical accelerations, and they look perfect, but that's because the simulation that I used apparently was written in a perfect way. It didn't allow for errors, I guess. So what that means now is that the theoretical acceleration matching the experimental acceleration, that this equation here, the net force equals mass times acceleration, predicts the correct acceleration because that was measured over here with the other equation, and so that means that Newton's second law is correct, at least for this experiment. The net force equals mass times acceleration. And as I said, for the other setups that I could use in the lab, it would be harder because friction is really hard to measure, hence the air track.